Welcome back to pattern matching. This is Daniel, and in this video we're basically going to exhaust all the patterns that you can possibly have in your code. As usual, let's go to part 4 pattern matching and actually create a Scala class. Let's call this all the patterns. Make this an object, of course. Extends app. So let's take all the patterns in turn. First of all, we have constants, which is basically the background for the switch on steroids. So if I say val x, specifically tied with the type any, so that I can prove my point, and the string is Scala, I can say constants equals x match, and then I can pass in any constant that I want. And constants can be, for example, plain values like 1, say a number, case a literal string like Scala, I'm going to say the Scala, and we can have literals true and false, say the truth. Amazing book, by the way. And case a singleton object, like all the patterns. So literals can be, or constants can be, a literal int, a literal string, a literal true or false, and any plain value plus a singleton object. So this is the simple switch on steroids part. Second pattern is wildcard. Actually not wildcard, but match anything. And an implementation of that is wildcard. Let me show you what I mean. So if I say val match anything is x match case underscore, and then I return whatever. From now on, I'll just leave out the return expression because I don't really care about the return expression. I only care about the cases here. Okay, so this is the wildcard. Now, there is also another way of matching anything by matching in a variable. So if I say match a variable is x match case something, and this something matches any value, but the property of this guy is that I can then use it in the return expression. Right? So I can use this value that was extracted later in the return expression. We've seen this in the previous video. Okay, now we can do pattern matching on tuples, for example, and on simple data structures. So I'm going to start with tuples. So if I say val a tuple is the tuple 1, 2, okay, then I can match a tuple. Let's say match a tuple equals a tuple match, and then I can pass in here for cases. I can pass in a literal tuple. A literal tuple is actually a stretch of a definition, but a tuple of literals. So for example, 1, 1. I can also pass in a tuple composed of nested patterns. So if I say case something and 2, then this guy will try to extract this something out of the tuple if the rest of the pattern matches. And then I can then use this something later in the returned expression. Okay, so we can have nested pattern matching. This also happens and is also possible with nested tuples. So if I define a value called nested tuple and say this is a tuple of 1 and the tuple 2, 3, so this is a nested tuple, then if I try to match a nested tuple is a nested tuple match, and I can pass in a nested tuple composed of nested patterns. So for example, I can pass in an underscore and another tuple with 2 and a variable v. And I can match this v even though it's inside of a nested tuple inside this whole pattern right over here. So pattern matching suddenly became more powerful. So you found that pattern matching or pattern matches can be nested, which is pretty darn cool. Now, speaking about tuples and simple data structures, we've already seen the biggest use case of pattern matching, which is case classes. This is called a constructor pattern. All right, so if I have a small mylist, which is a mylist of int. Yeah, exactly, the mylist that we implemented in the object-oriented section. So if I write this as a cons with 1 and cons 2 and empty, I need to actually import all of these. Then I can actually pattern match against this. So let's call this match a list. And this will be a list match. And inside, I can put in possible cases. So if it's empty, I can do something, or I can return something. And if I run a cons with a head and some kind of tail, let's run this tooltip out of the way, then I can return something else. Okay. So head and tail now are these variable pattern matching. So cons with a variable and a variable will bind the values that are extracted from a list. So in this case, head will be 1 and tail will be cons 2 empty. Okay. Case classes can also be nested. So if I run another cons in here, let's call this subhead and subtail. These can also be matched in a nested fashion. So head in this case will be 1, subhead will be 2, and subtail will be empty. Okay, so you notice that pattern matching can be nested with case classes as well. Next, an extremely powerful use case, list patterns. Like actual list patterns. Let's construct a standard list. Let's call this a standard list. And let's make a list of 1, 2, 3, and 42. Because I like 42. All right. And let's match against it. So let's call this standard list matching. And this is equal to a standard list match. And here are the patterns that I'm about to write. Case list with 1 and underscore and underscore and underscore. This is called an extractor for list. So even though list itself is not a case class, the list constructor extractor exists in the Scala standard library. This is advanced. And this does basically exactly what you would expect. It tries to match a standard list against a list of 4 things, in which 1 is the first element. All right. We can also have list of 1, and watch what I'm writing. Underscore star. This is a var arg pattern, which is a list of arbitrary length. This is also advanced. We can also have something which reads 1 : list of something. This is called an infix pattern. and a lot of magic goes under the hood so you can write something like this. And of course, you can have some other kind of infix patterns. If you get this one, you get others as well. So if I say list 1, 2, 3, colon plus 42, this is also an infix pattern. All right, so really powerful list patterns right over here. Use them wisely. Next, we have type specifiers, which I really didn't get into in the last video, but I will get into them now. So if I define a value, let's call this unknown, which is of type any, and I give this a value of say 2. And I want to pattern match against this. Let's call this unknown match equals unknown match, and I can say case list of type list of int. So this, the colon type, is a type specifier, and I can do whatever if the pattern matching matches fully, including the type. So this is an explicit type specifier. All right, so this is how you force pattern matching to conform to certain types. Next, we have what we call name binding, which is what happened with variables. So when you match variable, you match anything and you bind that to a name. But name binding here in this context means something else. This is an explicit name binding. Watch what I'm writing. So I'm going to write a pattern match. Let's call this name binding match equals a list, which is my list over here up top, match. And I'm going to say case cons with 2 underscores. But before that, I'm going to give that a name by saying not empty or non-empty list at. So this name at will name a pattern. This is a name binding, which makes you use the name later or here in the return expression, like you did with variables earlier. But the name binding is more powerful because you can name entire patterns here. All right. And name binding works inside nested expressions, nested patterns actually, as well. So if I say case cons with 1, and let's call this rest at cons 2 whatever, this rest at sub pattern will still work. So name binding inside nested patterns. Again, you can use this rest object later in the returned expression. All right, so this is pretty cool. Pattern matching is already becoming overwhelmingly powerful. All right, next we have multipatterns. Let's bring this up top. All right, multipatterns are multiple patterns chained by a pipe operator. Let me show you what I mean. So I'm going to make a little multi-pattern, and I'm still going to match a list, and I'm going to say case empty, or this is the pipe operator that I talked about, cons with 0 and whatever. This is an example. This is a compound pattern or multi-pattern. You can chain as many patterns as you want with this pipe operator when you want to return the same expressions for multiple patterns. All right. And finally, I'm leaving the if guards at the end. You've dealt with these before. So if I say second element, special. I'm still going to match against a list. And I'm going to test for the second element to be some kind of special, and say case cons with whatever and cons with a special element and whatever. And at the end, I'm going to say if special element mod 2 equals 0 or some other kind of predicate. Okay, so the if guard here will filter out the pattern by this predicate. And that, my folks, will be all. Now I have a question for you. Say, for example, I have a little numbers list, which is a list 1, 2, 3. Okay, pretty simple. Now, let's try to pattern match against this. I'm going to write the following. I'm going to say numbers match equals numbers match, and inside I'm going to put in two cases with typed cases. So I'm going to say case a list of strings, which is a list of strings, and I'm going to return a list of strings, and I'm going to put in a list of numbers, which is a list of int, and this returns a list of numbers. Right, so two very, very simple return expressions, and a case underscore just to cover my ass, and returns the empty string. Now, if I print line numbers match, pause the video and think about what do you think numbers match should look like. Now, if you think the correct answer is a list of numbers, normally you would be right, but here you're in for a surprise. Oh, I get matchers. Oh, that's because of all the examples I've given you. Let's just comment all of these so that I can prove my point. So run this, and we get a list of strings, my folks. Even though numbers is a list of int, the case matches against a list of strings. Why does that happen? This, my friends, is not Scala's fault. This is a JVM trick question. So, the long story short is that the JVM was designed for the Java language, but the Java language was also designed with backwards compatibility in mind. So basically a Java 9 program right now, or a Java 9 JVM, can run a Java 1 program written 20 years ago, which is pretty darn cool. I'll give them credit for that. But at Java 1, Java did not have generic parameters. Generics were introduced in Java 5. And to make the JVM compatible with Java 1, the Java 5 compiler erased all generic types after type checking, which makes the JVM absolutely oblivious to generic types. Scala also suffers from this fault because the JVM was designed in this way. So basically, after type checking, our pattern match expressions look like this, because our type parameters just are erased like that. And when the pattern match looks like this, then suddenly everything makes sense, because numbers is a list, and a list matches a list, which returns a list of strings. All right, this was a hard question, and this is something related to the JVM that you might want to keep in mind, especially if you design high-level generic APIs. This pain in the neck is called type erasure, and frameworks like Scala Z and Shapeless also suffer from erasure problems. All right, and the IDE is smart enough to actually warn me about this. So it says, fruitless type test, a value of type list of int cannot also be a list of string, but still might match its erasure, which it does, because if I erase its type, it will start to match. All right, we've seen enough patterns to last for a lifetime. I'm Daniel, and I will see you in the next video.